Aromatic substitution is essential for creating aryl halides. Today, we explore two primary methods for converting benzene diazonium salts into chlorobenzene or bromobenzene, the classic Sandmeyer reaction and its modification, the Gattermann reaction. Direct halogenation of benzene can be difficult to control for specific orientations. Diazonium salts act as versatile intermediates, allowing us to place halogens precisely where the nitrogen group once resided with high yield and purity. In the Sandmeyer reaction, we use copper, i.e. salts, such as cuprous chloride or cuprous bromide. These salts act as the source of the nucleophile and the catalyst, facilitating the displacement of nitrogen gas from the aromatic ring. The mechanism involves a single electron transfer from the copper ion to the diazonium cation. This creates an aryl radical and releases nitrogen gas. The radical then reacts with the halide to form the final product. The Gattermann reaction is a variation of the Sandmeyer process. Instead of using copper, i.e. salts, it utilizes finely divided copper powder in the presence of a halogen acid like HCl or HBr to achieve the same result. While both reactions yield the same organic products, the Sandmeyer reaction is typically preferred in industrial settings. It generally offers higher yields and faster reaction rates compared to the Gattermann modification using copper powder. Let's look at a specific example. To produce chlorobenzene via Sandmeyer, we react benzene diazonium chloride with cuprous chloride in hydrochloric acid. The evolution of nitrogen gas drives the reaction to completion. Using the Gattermann method for the same product, we use copper powder and HCl. Notice that the yield is significantly lower. The copper powder reacts with the acid to generate the copper ions required for the mechanism in situ. The same logic applies to bromination. Using cuprous bromide constitutes the Sandmeyer reaction, while using copper powder in hydrobromic acid is the Gattermann reaction. Both pathways successfully replace the diazonium group with a bromine atom. Why is Sandmeyer usually better? The preformed cuprous salts are more effective at electron transfer than the surface of copper powder. This leads to fewer side reactions and a more consistent output in laboratory settings. Temperature control is critical for both reactions. Diazonium salts are highly unstable and can decompose into phenols if the temperature rises above 5 degrees Celsius. Always keep the reaction mixture chilled during the initial stages. To summarize our comparison, Sandmeyer uses copper, i.e. salts, while Gattermann uses copper powder. Sandmeyer provides superior yields and is the standard choice for synthesizing aryl halides from diazonium precursors. Remember these 3 points: both reactions are used for aromatic substitution, both rely on the release of nitrogen gas as a driving force, but the Sandmeyer reaction is the more efficient chemical route. Let's test your knowledge. Which reagent is used specifically in the Gattermann reaction to produce bromobenzene? Think about the catalyst form we discussed earlier. The correct answer is B. Gattermann reactions always utilize freshly prepared copper powder in the presence of the corresponding halogen acid, whereas option A would be the Sandmeyer condition. From a practical standpoint, the Gattermann reaction requires the filtration of solid copper powder at the end, while Sandmeyer catalysts are often easier to handle in solution, further contributing to its popularity. Understanding these reactions allows chemists to build complex molecules with precision. Whether using Sandmeyer or Gattermann, the diazonium intermediate remains a cornerstone of organic synthesis. Thank you for watching this lesson generated by Vision Solve AI.